Section 5.3, Evaluating Definite Integrals. In Section 5.2, we computed integrals from the definition as a limit of Riemann sums, and we saw that this procedure is sometimes long and difficult. Sir Isaac Newton discovered a much simpler method for evaluating integrals, and a few years later, Leibniz made the same discovery. They realized that they could calculate the integral of the function f of x dx from a to b if they happened to know an antiderivative f of the function f. Their discovery, called the Evaluation Theorem, is part of the fundamental theorem of calculus, which is discussed in the next section. So here's the Evaluation Theorem. If f is continuous on the closed interval from a to b, then we can say that for this integral, the f of b, meaning the antiderivative evaluated at b, minus the antiderivative f evaluated at a, where f is any antiderivative of f, and that is f prime is equal to the function f. Now, this theorem states that if we know an antiderivative f of f, then we can evaluate this integral simply by subtracting the values of the antiderivative at the endpoints of the closed interval from a to b. It is very surprising that the integral, which was defined by a complicated procedure involving all the values of f of x for when x is in between a and b inclusive, can be found by knowing the values of the derivative at only 2 points a and b. So for instance, we know from section 4.8 that an antiderivative of the function f of x is equal to x squared is 1/3 x cubed. So the evaluation theorem tells us the following. So we know that we have the integral from 0 to 1 of that function x squared dx. Okay, so the antiderivative of x squared is actually 1/3 x cubed. And so then what we do is we create this little segment here, and then we evaluate it after we take the antiderivative from the lower limit of 1 to the upper limit 0 to the upper limit of 1. And so then what we do is then we apply these limits. So we're going to take the antiderivative at the input of 1 minus the antiderivative at the input of 0. So what that tells us is we end up getting 1/3 times 1 cubed minus 1/3 times 0 cubed. Okay, and what that ends up giving us is the following. We end up getting 1/3 minus 0, which equals 1/3. And so therefore, that allows us to evaluate this integral. So as we proceed further, we will see how this is written out, just like we did here. Now, comparing this method with the calculation in example 2 in section 5.1, where we found the area under the parabola y equals x squared from 0 to 1 by computing a limit of sums, we see that the evaluation theorem provides us with a simple and powerful method. Although the evaluation theorem may be surprising at first glance, it becomes plausible if we interpret it in physical terms. Now, if v of t is the velocity of an object and s of t is its position at time t, then we know that v of t is equal to s prime of t, which is the derivative of the position function. So s is an antiderivative of v. So in section 5.1, we considered an object that always moves in the positive direction and made the guess that the area under the velocity curve is equal to the distance traveled. So in symbols, we can say that the integral, okay, that goes from a to b of the velocity function dt is equal to s of b minus s of a. So you see here that we always start with the upper limit as the input and then subtract the lower limit as the input. This is exactly what the evaluation theorem says in this context. Now, the proof of the evaluation theorem. We divide the interval, the closed interval from a to b, into n subintervals with the endpoints going from x subscript 0, which is the a, all the way to x subscript n, which is equal to b. and with the length delta x, which is equal to b minus a divided by n. So if we let capital F be any antiderivative of the function lowercase f, by subtracting and adding like terms, we can express the total difference in the f values as the sum of the differences over the subintervals. So f of b minus f of a is equal to f of xn minus f of x0, which is the upper and lower limits, which is equal to f of xn minus f of xn minus 1 plus f of xn minus 1 minus f of xn minus 2, and so on, all the way to f of x2 minus f of x1 plus f of x1 minus f of x0. And what this equals is the summation of I is equal to 1 to the power of n of f of x subscript I minus f of x subscript I minus 1. Now, f, the antiderivative, is continuous because it's differentiable, and so we can apply the mean value theorem of the antiderivative on each subinterval. Thus, there exists a number, which is those sample points, the ith sample points, between x subscript I minus 1 and x subscript I, such that we have the following. F of x subscript I minus f of x subscript I minus 1 is then equal to the derivative of that sample of I input times xi minus xi subscript 1 minus 1, which is equal to the height times the width. Therefore, we can say that f of b minus f of a is going to equal the sum from I is equal to 1 to n of the height times the width. Okay, now we take the limit of each side of this function as n approaches infinity. The left side is a constant, and the right side is a Riemann sum for the function f. So we can say f of b minus f of a is equal to the limit as n approaches infinity of the sum of the height times the width, which then equals the integral of the function f of x dx from a to b. When applying the evaluation theorem, we use the notation as I showed you in the previous example. The antiderivative f of x going from a to b is equal to f of b minus f of a. And so we can write the following. The integral of f of x dx from a to b is equal to the antiderivative from a to b, where we know that the antiderivative is equal to the function. Other common notations are the following. You're going to see the antiderivative of x that has a line here going from a to b, or we can put this in brackets, which that function goes from a to b.